Hello again. At this point, we've gotten pretty good at looking at derivatives of power functions when we have a variable base and some exponent, any real number exponent. We've used that to determine derivatives of polynomials. We've got the product and quotient rules when we have the product of multiple functions or the quotient of multiple functions. And we have the derivative of exponential functions, namely base e. Right now, we start moving on into additional functions, and we're going to be looking at derivatives of trigonometric functions. Specifically sine of x, cosine of x, tangent of x, and then the reciprocals cosecant of x, secant of x, and cotangent of x. We're going to be tying back in with some of our trigonometric identities. Now, you need to know the Pythagorean identity. It's always a good idea to remember that sine squared plus cosine squared is 1. The others are not essential. They help, but it's not absolutely mandatory for this. I will be bringing them up as we go along. So we look at here, I've got the graph of sine of x. Let's think about what is the graph of the derivative. So how can we kind of infer what this should be? I'm going to take our tangent lines. I'm going to start off looking right around 0. Like, okay, there's a tangent line. That looks like we've got a slope of about 1. At pi over 2, well, we've got a slope of 0. At pi, we've got a slope, it looks like negative 1. At 3 pi over 2, we've got a slope of 0. And then 2 pi, we've got a slope of 1. And it repeats. Let's look at our slope now. If we put those numerical values, try to graph them. So m equals 1. And here's why. Always use radians. You're in calculus, you're in math, use radians. So at 0 radians, our slope is 1. So our derivative of x would be 1. At pi over 2, our slope of the tangent line would be 0. So the slope of the derivative, would be 0. At pi, our slope looks like it's negative 1. So our derivative would be at negative 1. 3 pi over 2, our slope is 0. So our derivative is going to be back to 0. At 2 pi, we repeat that process. Our slope is back to being 1. And we could see that with the sinusoidal, with a periodic nature to sine, we would have this repetition forward and backwards. Okay, connect those points. Our derivative, we would expect to look like this. That green graph in there, that looks like an awful lot like cosine of x. So graphically, numerically, kind of estimating the derivative, it should be cosine. Now let's go on and prove it. Applying our limit definitions of the derivative. Looking at that first definition, the limit as x approaches a of sine of x minus sine of a all over x minus a. I don't think we'd be able to factor that x minus a term. And it would be any easier to factor h, because that's a polynomial linear term out of a transcendental function, one that is not represented by a polynomial. But I'm going to go on and use our second definition. Now, what can we do here? I notice that the first, sine of x plus h, that we have an identity for. If we think back to past experiences, sine of a plus b, that's sine of a cosine of b plus sine b cosine of a. That is our sine sum formula. So this gives us the limit as h approaches 0. That can be represented as sine x cosine h added sine h cosine x minus sine x all over h. I'm going to group some things here together. We've got this sine of x minus sine of x. I'm going to factor that. We've got limit as h approaches 0 of sine of x. That will leave us with cosine of h minus 1 plus sine h cos x over h. Look at these as two separate limits. This gives us the limit as h approaches 0 of sine of x cosine of h minus 1 over h plus the limit as h approaches 0 of sine of x, cosine of x multiplied by sine of h over h. So that's sine of h over h. Limit as h approaches 0 of sine of h over h. That approaches 1. We just have cosine. Cosine h minus 1 over h. That approaches 0. And we can see that if we multiply by the conjugate cosine x plus 1 over cosine h plus 1 over cosine h plus 1, that would give us cosine squared minus 1, which is negative sine over cosine h plus 1. That negative sine squared, as h approaches 0, is going to go to 0. So that whole first term is 0. We're left with just cosine of x. So it turns out that the derivative of sine of x is cosine of x. Hooray! Let's look at cosine while we're here. Now we've got that same sum formula there, the cosine sum formula, so cosine A plus B, that is equal to cosine A, cosine B, subtract sine A, sine B. Those are your trig identities. You should have seen that in pre-calculus. I'm not expecting you to remember that, just, hey, that's a thing, there we can use it. So expanding, we've got limit as h approaches 0. This will be cosine x, cosine h. Subtract sine x, sine h. Subtract cosine x all over h. With some convenient factoring now, we've got that cosine x term, that cosine x term. It's going to give us limit as h approaches 0. This will be cosine of x. That's a cosine h, subtract 1 over h. I ran out of room. Will be minus the limit as h approaches 0 of sine x times sine of h over h. There's that minus sine x, sine h over h, minus, that's that minus. Took out that cosine, left with cos h minus 1. Now, take a look. First term, cos h minus 1 over h, that approaches 0, so that whole term is eliminated. Sine h over h, as h approaches 0, that approaches 1. And we are left with negative sine of x. Ooh, curious. So let's compile this. What we've seen is now that the derivative of sine of x is equal to the cosine of x. The derivative of the cosine of x is equal to negative sine x. And thinking about the graph, just how we can see that. There's cosine. Well, derivative would be 0, negative 1, 0, positive 1 slope, back to 0. Connects back to graph of negative sine. So there's this cyclical nature that if f of x is equal to sine of x, the derivative of sine of x, I'll put it this way, if we do the derivative of sine of x, gets us cosine of x. If we take the derivative of cosine of x, it gets us negative sine of x. If we take the derivative of negative sine of x, what would be the opposite of the derivative of sine of x, giving us negative cosine of x? And if we take the derivative of negative cosine of x, it would be the opposite of the derivative of cosine of x, would be negative sine x, would give us sine of x. There's this 4-element cycle that it rotates between. Remember back to Algebra 2, imaginary numbers? There's that 4-element cycle, just like that. So let's see this in action. Here's our first example. I'm going to differentiate y equals x squared sine x. The first thing I notice is that this is a product. We need to impose the product rule. Remember that d dx of a product uv, that's derivative of the first multiplied by the second, add the derivative of the second multiplied by the first. So our first is x squared, our second is sine of x. That's going to give us dy dx. Derivative of x squared is 2x, multiplied by the second is just multiplied by sine of x. Added to that, the derivative of the second derivative of sine of x is cosine of x, multiplied by the first, x squared. It's typical that we're going to write any product with a trig function in front, so we're not confusing like x times x squared. Is that actually supposed to be x cubed? I'm going to write it so our function ends up in front. There's a derivative. Let's try those other functions. Tangent now. Now, deriving this, I'm going to recall the tangent can be rewritten as sine over cosine. That's a quotient, using our quotient identity. Now, derivative of a quotient, remember, d dx of u over v is derivative of the top times the bottom. Subtract the derivative of the bottom, multiply by the top, all over the bottom squared. So that's going to give us derivative of the top. Sine of x is going to be cosine of x multiplied by the bottom, multiplied by cosine of x, subtract the derivative of the bottom. So derivative of cosine of x is negative sine of x. Oh, that's going to be add sine of x multiplied by the top is sine of x. Oh, that is happy days. All over the bottom squared, all over of cosine squared. What I noticed there, that's cosine squared plus sine squared. That's 1. We have 1 divided by cosine squared. Well, over cosine squared, that's just secant squared. So the derivative of tangent turns into secant squared of x. Now, let's take a look at secant. Oh, I might think that something's going to happen here. Now, I remember secant, that is 1 over cosine. Remember, secant is the reciprocal of cosine. I'm going to apply the quotient rule. My numerator is 1, my denominator is cosine. So we're going to have derivative of the top. Derivative of 1 is 0. I'm just going to write it out 0 times cosine of x. Subtract the derivative of the bottom. It's going to be negative sine x multiplied by the top, multiplied by 1, all over the denominator squared, cosine squared. So this gets us sine x over cosine squared, which I can break apart as sine x over cos x times cos x. Sine over cosine, that's tangent. And then 1 over cosine, that's secant. So the derivative of secant, let me just switch that around, is secant multiplied by tangent. This is, of course, wherever the function is defined, so we need to know the domain of secant of tangent. So the derivative of secant is not just tangent, but the derivative is secant times tangent. We're going to do similar things for cotangent. In fact, I'll leave this to you so you can work through the derivation on your own. Derivative of tangent up top is secant squared. This is going to be a nice relation. Cotangent is going to be negative cosecant squared. Derivative of cosecant would work similar to secant, except that is going to be negative cosecant x cotangent x. I like to remember a little device. C stays with the C's, and also C stands for change. So I've changed the signs. S-I-G-N, positive, negative. It's one little way that I help remember these. These are derivative rules. You need to remember these. Put these into the memory banks. Put them on speed dial. Put them in your contact lists or whatever we do nowadays. Remember these. Let's see some things in action. Differentiate the function. Find the values of x for which the graph has a horizontal tangent. Just reminding ourselves that would be f prime is equal to 0. Horizontal tangent, horizontal line is a slope of 0. Now I notice quotient rule. Remember d dx, quotient, u prime v minus v prime u all over v squared. So applying our quotient rule to this function, derivative of the top, so derivative of secant squared, that is secant x tan x. Just going to remind myself, d dx of tan, that is secant squared. So applying our quotient rule, derivative of secant squared, we're going to have secant x tan x multiplied by the bottom, 1 plus tan x. Subtract the derivative of the bottom, derivative of 1 plus tangent is just going to be secant squared. Multiplied by the top is secant, all over the bottom squared. Neatening things up a little bit, we have f prime of x. That is, only going to, how am I going to do this? We're going to have secant x tan x plus secant x tan squared minus secant cubed all over 1 plus tan x squared. Let's see if we can factor secant out of that. So it would be secant, that's going to be tan x plus tangent squared minus secant squared. 1 plus tan squared. Now here I remember tangent squared minus secant squared. That's one of our Pythagorean identities. That is equal to 1 plus tan squared secant. That's equal to -1. That's equal to -1. Whoopsie. That's equal to -1. And so we have one more step, neatening things up. That's got f prime of x. That's secant. I've got tan x minus 1 over 1 plus tan x squared. Now we want to know, when is this equal to 0? When do we have horizontal tangents? Back up to the top. We would look at each factor in the numerator, set each factor in the numerator equal to 0. I'm going to slide this over. Secant equals 0 does not exist. Think about the graph of secant. Then we've got tan x minus 1 equals 0. Tan x equals 1. That's going to be at pi over 4. And every pi k. Let's do a little bit more. Two more. Option. Item. Weird about it right there. The end of a vertical spring is stretched 4 centimeters beyond its rest point, pulled down and released at time 0. So I'm going to pull this item down 4 centimeters, and it's going to pop back up. So it's going to go up and down and up and down and up and up and down. Downward direction is positive, so we're starting off with a distance, a displacement of 4 centimeters. Position of the spring at time t is given by this position function. S, position equals f of t equals 4 cosine t. I want to find the velocity and acceleration at some time t, and think, how does that connect to our graph and to the motion of the object? So derivatives, so if s is 4 cosine t, we know that the derivative of position is velocity. So the derivative is going to be, well, derivative of cosine is negative sine, so we've got -4 sine t. The second derivative is our acceleration. It's the derivative of velocity. So the derivative of -4 sine t, I'm thinking the derivative of negative sine t is going to be -4 cosine t. Now in context, looking at the graph, we've got s. We start 4 centimeters down. It's going to bob up to the equilibrium point, up to a maximum, back down to the equilibrium, back up. Thinking that to compare to the velocity, at the very start, we've got 0 velocity, but it's going to have negative velocity because we are moving away. We're moving back up, away from +4, until we get to the equilibrium part, and then our velocity is going to start decreasing, or actually increasing to becoming a positive velocity. Once we hit the maximum, the peak at the top, velocity would be 0, and we start going back down to reach. Acceleration works just the same. Notice that there's a connection. When we're starting off, we're starting with 0 velocity, but our acceleration is accelerating the most into that negative direction, up in this case. When our object is at equilibrium, it's the greatest negative velocity, so it's speeding up at the fastest, but the acceleration is also pausing, because then the acceleration starts moving down. One last example that we've got, I saved the best for last. Well, our function is cosine of x. I want the 27th derivative. So the next 27 minutes of the video are going to be taking the derivative over and over and over again. And actually, I made a note earlier that the derivative of cosine of x, we know that is negative sine of x. We know the derivative of negative sine of x is negative cosine of x. We know the derivative of negative cosine of x is positive sine of x. The derivative of positive sine of x is cosine of x. And we'd be right back to the start. So that'd be the first derivative, the second derivative, the third derivative. The fourth derivative is right back to the start. This was like the powers of I back in Algebra 2. So every time we take 4 derivatives, we're back to the start. Rather than computing and computing and computing, we want the 27th derivative. If we divide that by the cycle of 4 elements, well, that's going to get us 6 with a remainder of 3. We call this the modular arithmetic. So the 27 mod 4 equivalent to 3, meaning the remainder. If we take 27, what's the remainder when we divide it by 4? Sometimes known as clock arithmetic. What that means is we're going to go through 6 full cycles and then 3 additional placements. So what we really want is just the third derivative. It's equivalent to that. The 27th derivative is, in fact, just 1, 2, what do I do there? It's just sine of x. That would be our first, that's our second, that's our third derivative, that's our fourth derivative, which is back to the start. So our third derivative, there we go.